Okay, in last class we have discussed about the characteristics of ideal filter, and we have also seen the group delay and also called envelope delay of the filter and its relation with the phase of the filter, right? So again we will go back to the ideal filter properties and start our evaluation from that particular point. So we'll go back again to properties of ideal filter. So first part is filter should have constant gain over passband. Second is filter should have zero gain over stop band. Sorry. Third is filter should have linear phase response. Linear phase response. And now we will see and discuss these three important properties of ideal filter. First case is ideal filter should have a constant gain over a passband. This property we have already seen when we have designed designed the frequency domain characteristics of ideal filter, and we have seen that over a passband it should allow all frequencies to be passed, and if without scaling then it should be ideally constant gain should be ideally equal to 1, right? So in the case of stop band, ideal filter should not allow any kind of frequency to pass through it, right? So it will not allow any kind of frequency. So the most important point is the filter should have zero gain over there. So when x omega will be multiplied with h omega, the overall resultant at that particular frequency will be 0, right? So it will act as a stop band. Now the important third point is filter should have a linear phase response. Why we want to say linear phase response? As we have seen in last class, if phase is not linear, right? If phase is not linear, then this tau g omega is also not linear. If phase is not linear, then tau g omega is also non-linear. That is, frequency will go through frequencies will go through a delay which is not constant in nature. Sure. That means our filter will distort. In this case, output of the filter is distorted, right? So it is very important for us to understand that our filter should have a linear phase. That means minus of del theta omega by del omega equals to tau g omega, right? This property of our filter, which gives us a group delay, should be constant. right? Okay. Next, we will want to discuss about the impact of the filter and is it realizable or not realizable. For that particular case, we are taking low pass filter, that is LPF. So its characteristics will be like this. So I'll plot a characteristics of a low pass filter. So we want to realize this particular filter and want to see its characteristics. It is minus pi to pi in frequency domain and mod of h omega its magnitude. It has a constant gain, so we'll say it is 1, and it allows frequency from minus omega c to omega c. Okay, so this is our LPF. We want to evaluate this particular thing. So this is our h omega. So we want to find out the value of hn. So we know hn is 1 by 2 pi minus pi to pi h of omega exponential j omega n del of omega, right? So then by seeing this particular part that h omega is only defined from in between minus omega c to omega c, so we can rewrite this equation. Find minus omega c to omega c h of omega exponential j omega n d omega. From minus omega c to omega c, h of omega is equal to 1, right? So then we can write this equation as 1 by 2 pi minus omega c to omega c exponential j omega n d omega, right? Now we can integrate this particular relation and we can find out it is 1 by 2 pi jn, right? And this is exponential j omega n minus of omega c to omega c. Okay, and this will come out to be 1 by 2 pi jn exponential j omega c n minus of exponential minus j omega c, right? So by arranging this equation you can easily see this 1 by 2 j exponential j omega c n minus exponential minus j omega c n is nothing but sine of omega c n over 2j is gone, then we have pi m, where this n is defined from minus infinity to n. Then if we multiply with omega c this complete equation at numerator and denominator, then it will be omega c over pi and sine of omega c n over omega c n, again from minus infinity and to infinity. Then one can say that hn is defined as omega c by pi for n equals to 0 and omega c by pi sine omega c n by omega c n for all okay. Now if we want to plot these characteristics, let's say for frequency omega c is equal to pi by 4. For this particular omega we want to plot this particular case, then hn will omega c is equal to pi by 4, then hn will be equal to 1 by 4 at n is equal to 0 and 1 by 4 sine pi by 4 n over pi by 4, right, for all other. So now if you want to plot this particular function of hn, we can do that, right? So we know it is a sinc function. So it goes from minus infinity to infinity for n, right? So we have this function hn at n is equal to 0, its value is 0.25, right? And one can see this sine pi by 4 n. I'll write it like this: sine pi by 4 n will decide when this function will go to 0 and negative, because this pi by 4 n will be positive and then this negative will come out to be positive again. So this negative and this negative, then they will come out to be again positive. So for one cycle it will remain positive, for another cycle it will remain negative, and it will goes on like that. So but zero crossing will be happen due to this function. So one can see when n is a multiple of 4, then only this function will go to 0, right? So first zero crossing will come at minus 4 and 4, then minus 8 and 8, and so on, then 16 and so on. So we'll just plot this particular function like this. As one can see, the value of sine pi by 4 n will mostly lie between minus 1 to 1, whereas this pi by 4 n will keep on increasing as the value of n will increase. As the value of n will increase, that's when this particular signal will damp over a time with n, right? So it will goes like this. Same here, this will goes like this. Actually that will be a kind of mirror signal in both sides, equivalent to each other, right? So it will go like this, cross at this, and then so on. So we will have this value at this particular position, n equals to 1, 2, oh, sorry, I have drawn it too much. So actually there will be only 3 sequences in between. So there will be only 3 sequences in between. So I'll just draw those 3 sequences. So 1, 0, 1, 2, and 3. So 1 is at this particular position, then 2, and then 3, and then 1, 2, and 3. And same way 5, 6, 7, 5, 6, 7, right? So so now this is the transfer function of filter in time domain. Now, is that function is realizable? No, actually, why not? Because this signal Hn is not causal. It's not causal signal. So it is not a causal signal. That's why it is not a realizable. And further, it cannot be realized in actual practices. Why? Because it is also not summable, thus making this filter unstable. So due to these two important points, an ideal filter is not physically realizable. Okay, so we'll discuss about this particular point about the causality in further classes. Thank you.